Today I am going to calculate friction factor from Colebrook equation and then use that friction factor to calculate pressure drop. Now here, to calculate friction factor from Colebrook equation, we have to use Newton-Raphson method, and after getting that friction factor we will put that friction factor into the del P equation and we will get the pressure drop. Now here is the problem. So problem is the pressure drop in a section of a pipe can be calculated as del P is equal to F L rho V square by 2D, where del P is the pressure drop, Pascal, F is the friction factor, L is the length of the pipe in meter, rho is density kg per meter cube, V is velocity meter per second, D is diameter of the pipe. For turbulent flow, the Colebrook equation provides a means to calculate the friction factor. Here 1 by root F is equal to minus 2.0 log epsilon by 3.7 D plus 2.51 Re to the power F, where epsilon is equal to roughness and Re is the Reynolds number. Re, you know that rho Vd by mu, where mu is the dynamic viscosity, Newton second per meter square. So here we have to calculate del P for 2 meter long horizontal stretch of smooth drawn tubing, given that rho is equal to 1.23 kg per meter cube, mu is 1.79 into 10 to the power minus 5 Newton second meter square, then diameter is given 0.006 meter, velocity is given 45 meter per second, and epsilon is given 0.0015 meter. And for Newton-Raphson method, so we need initial guess. So note that in smooth pipe with Re less than 10 to the power 5, a good initial guess for Newton-Raphson method can be obtained using Blasius formula, that is given F is equal to 0.316 Re to the power 0.25. Now this is the problem. So here we have to calculate del P, and for that we need that friction factor. Now how do we solve this problem? So first, what is the aim? Aim is to calculate the pressure drop in the section of pipe. So pressure drop equation is given. So del P is equal to F L rho V square by 2D. Now if you look at the problem, that length is given. So length is given. So that is 0.2 meter. Density is given 1.23 kg per meter cube. Mu is given 1.79 into 10 to the power minus 5. D is given. So that is 0.006 meter. Velocity is given. Okay, and epsilon is given, so that is meter. Now sometimes it's in millimeter, so you can convert that, right? And del P, so now we can calculate the del P. Now del P, so what are the unknowns? So L is known, rho is known, V square is known, D is known, but F is unknown. So we have to calculate the F, right? So that F can be calculated by Colebrook equation. Now that equation is given 1 by root F is equal to minus 2 log epsilon 3.7 D plus 2.51 by Re into root F, right? So this is the equation. So this is a very non-linear equation. Now we have to solve this equation by using Newton-Raphson method, and then we can get that F. Okay, so from this equation we will get F. Now that F we plug here and we will get del P. Now how do we get that F? So that I'll discuss in the next slide. Now here Reynolds number. So for this equation, so epsilon is given, D is given. Now we have to calculate Re. Okay, so Re, that is rho V D by mu. So if we plug all these values, so we will get Re. Okay. Now I'm talking about Newton-Raphson method. So if you know the Taylor series expansion, so fx0 plus h is nothing but fx0 plus h by factorial 1 dfx0 by dx, h square by factorial 2 del square fx0 by dx square. Now if you ignore second order term, why? So if h is very small, then this term will be, we can neglect, means this term will be small and the rest of the term will be very small. So now here if we ignore second order term, so we'll have fx0 is equal to fx0 plus h is equal to fx0 h by factorial 1 dfx0 by dx, right? Now here that at x0 plus h, if fx0 plus h is equal to 0, then fx0 plus h is the root of the equation. Now if we plot that, suppose this is fx. Okay, now if I draw this, okay, so now this is x and this is y. Okay, and this is that x is equal to means y is equal to 0 means this is x axis. Now if that this is fx, now if so this suppose this is x0 plus h. Okay, now at this point, so your function value is fx0 plus h is equal to 0, so that will be the root of the equation. Okay, so now we have to calculate what is the x0 plus h, correct? So now we just assume that x1 is nothing but x0 plus h. Now if we ignore this term, so we have this term, and if we plug x0 plus h, so this term will be 0. So now from here, so fx0 plus h is equal to fx0 plus h df x0 by factorial 1 dx. Now f x0 plus h, so here that is 0, right? So we'll get fx0 plus h df x0 by dx is equal to 0. So from here we can easily calculate the h. Okay, so h is nothing but minus fx0 by df x0 by dx. Now if I know the h and if we know the initial guess, so we can easily calculate that the root of the equation x1, right? So x1 will be nothing but x0 minus fx0 by df x0 by dx. So this is actually Newton-Raphson method. By using that Newton-Raphson method, so we can write in the good way. So x1 is x0 minus fx0 df x0 by dx. Now if that xn plus, if I write in n number of iteration means generic formula, so that is xn plus 1 is equal to xn minus fxn df xn by dx. Okay, now if I put n is equal to 0, so similar x1 minus x0 minus fx0 df x0 by dx means if we have the equation fx is equal to something x cube minus 2x plus 6. So now by using you can use the formula, we can easily get the root of the equation. Now here, so we have to do the iteration, right? So when will be the iteration stop? Now when that we know, right, f xn plus 1, when it will be tends to 0, okay, it tends to 0, so we can stop the iteration. Or maybe if it is a very small value like 10 to the power minus 6, then we can stop the iteration. So this is the basic of Newton-Raphson method. Now coming back to the that friction factor calculation by Newton-Raphson method. So we have this equation, right? Okay. Now so if we put all these parameters, what parameters are given, so 1 by root f minus 2 log and epsilon is given, so that is 0.0015 meter, 3.7 into, so this is actually 6, okay, 3.7 is to d, okay, and then 2.51 rho vd by mu, so we put that Reynolds number and then root f, right? If we plug all these value, so if we plug all these value, ultimately we will get, so here, so 1 by root f is equal to minus 2.0 log of 0.06758 plus 1.3 into 10 to the power minus 4 1 by root f. Now if we put in the right hand side, so not right hand side, left hand side, so 1 by root f plus 2 log this equation, so that is equal to 0. So this is the function of it, right? So I'm function I'm writing in the capital F, as that f we have to calculate. So f is the f we have to calculate. Okay, so that will be the root of the equation. So f of f will be 0, means if we get that f, okay, and that f, if f is equal to 0, f of f is equal to 0, so that will be the root of the equation. Now this is the that linear equation, sorry, non-linear equation. So these are the non-linear equation. Now we have to solve by using Newton-Raphson method, and we will get that f, root of the equation. Now how do you solve that? Now this is the equation, right? So now f is equal to 1 by root f 2.0 log this, right? Now first, so if we use Newton-Raphson method, means we have to calculate that friction factor, as this f of f is a nonlinear equation. So first we need to have we need that we need initial guess. So now initial guess, if that RE less than 10 to the power 5, so f is Blassius equation formula, so that f is equal to 0.0316 RE to the power 0.025. So that is the initial guess. Now we know that RE, okay, so RE we can calculate that RE. So now we can get that from the Blasier's formula, so that we can get 0.0436. 0.36. I think that RE is here something wrong, maybe. That is nothing but 1.855855 into 10 to the power 4. Okay, check the calculation. So the procedure is okay. So this is the RE value, and F will be F also not that correct. So that will be 11 point something. Okay, so that will be nothing but 0 point something 0276. So we will calculate that by using MATLAB. Okay, so by using MATLAB we will get all these correct value. Now we have that FF is equal to this. Okay, now using Newton-Raphson method, so we know xn plus 1 xn is equal to that f of xn df xn. Now here function is nothing but we are putting as a capital F. So f1 is like a the root. Okay, so f1 is equal to f0. So if n is equal to 0, so that will be f1, and x here, x is nothing but f. So f1 is equal to f0 minus f of f0 df f0 by df. So now here we have to calculate that the derivative of this. You can do the derivative, or you can use central difference. So central difference is f of f0 plus h minus f of f0 minus h by 2h. So using that we can easily get the derivative of the function. Okay, so function at point f0. So we can do that. Now so for here h is very small. If you take very small, then only you will get that the derivative. Okay, so now here everything is you can easily get that. So this is a function. Okay, and we calculate f0, right? So here is the correct value. So that is 0.0207. Now from if we plug f of f0, we'll get this value, right? And then we can also calculate the derivative. So this is the derivative. Okay, so we have f0 plus h. So we plug all this value. Ultimately, we can calculate. So we already know function, right? F of f is equal to 1 by root 7. This total whole equation is there. Now if you plug that f of 0.02716 minus f of 0.02696 by 0.002, so we can easily calculate the derivative, right? So now here we are calculating that function 0.027176 and 0.0296. So we got 3.7360, 3.7585. Now if we plug all these value, okay, if we plug all these value, so this is 0.2706. So this is actually 0.27 something 27, and this value 0.27 0.027 0.0276. Okay, so that is there. If you put all together, so that will be that will give the derivative. Okay, now using Newton-Raphson method, so we know this value again initial value we know. So from that we can calculate the f1. So f1 is nothing but 0.0604083, right? Now if you calculate f of f1, so that will give 1.73518211, right? Now so that is, it is not equal to 10 to the power minus 6, or not near equal to that 0, right? So then we have to take that f1 as a initial guess, and then we have to do the calculation. Again we will do that calculation, and when we'll that criteria, when this criteria will satisfy, then we'll stop the iteration. Now here is the cumulative that calculation. Now initially we take that fn is equal to 0.027076 initial guess. Then we have to calculate that f of fn, so that is 1.735. Then we calculate derivative. Then this is the inner method. Okay, and then we are checking whether that is close to 0 or very less value, means it is nearly near value is 10 to the power minus 6. So if that is satisfied, then we can say this is our the friction factor. Now here I did that, so several iterations, 6 iterations. So we found that after 6 iterations, So when that friction factor is 0.18318073, so that f of fn plus 1 is close to 10 to the power minus 6. Now if you do that, so now we got that friction factor, and then we plug this value friction factor, so 0.18318073 into that L is 0.2, and then density is 1.23, and the B is 45 square, and then 2 into D is 0.006, so we will get that Pascal. That is the pressure drop. Okay, so we get that pressure drop. Okay, so this is the hand calculation. By using hand calculation, we will get that. Now coming to that MATLAB programming, right? So using MATLAB program, we can also get the friction factor, and also then after that, after getting the friction factor, we can do the pressure drop, the calculation. Calculate in MATLAB. Okay, so first you have so I'm using that Octave. Octave and MATLAB is very similar. So by using Octave, so we can solve this problem. Okay, now here, so first you have to put CLC, means clear skin, and then CLC, and then put that clear all, means if there is some storing variable, so that will clear all. So now next will be okay, so we are doing the Newton-Raphson method, so we can put that Newton-Raphson method, so that we can write that Newton-Raphson method. So I am using very I'm doing I'm writing that very simple code. That is command I am giving the Newton-Raphson method. Then first we have to assign the variable given parameter. So given parameter or variable, given parameter we can write given parameter. Okay, now here that L is given, so L is actually 0.2, that is given. Okay, and then rho is given. Rho is actually 1.23, that is kg per meter cube, that is given. Then D is given. D is actually 0.006, that is given, that is in meter. And then what are given? Then velocity is given. Velocity is 0.45, sorry, not 0.45, 45 meter per second, so that is given. And then that epsilon, the roughness factor, so epsilon EPS, we use that EPS, so that is 0.0015. Okay, so we can vary that epsilon, and we can calculate the pressure drop. So that is in meter. We can write in meter. Okay, we can vary that. And then now these are the variable actually given, right? Now we can calculate the Reynolds number first. So calculate Reynolds number. Okay, so first we have to calculate the Reynolds number. So Reynolds number, we know that RE is equal to what? D into V into rho by mu. So mu we didn't assign here, so we have to assign mu. So in my mu is here, that is given 1.79 into 10 to the power minus 5. So E minus 5, so that is 10 to the power minus 5. So Newton second per meter square. Okay, so we can write that. Okay, so for that here we have to assign that. Okay, so this. Now if we calculate that, so we have to run that. So run. So now here we have to assign some variable, right? Okay, so we can download. So in our method. Okay, so if we do that, and change the directory. So we'll get, so here, so L is 0.2, rho is 1.2300, and then these 6 e to the power minus 3, V is 45. Now we can get 1.855 e to the power 4. So now we got the Reynolds number. Now we can calculate the initial guess. So initial guess from the Blasius equation, initial guess, guess. So that we can calculate by using the formula. So F is equal to 0.316 by RE to the power 0.25. So we can, if we do that again, if we run, so we can see that F is 0.27076. So we can get that. Now so initial guess Reynolds number we got. Okay, now first we have to create that function. Okay, so there is a various way to create function. So I'm showing this is the inline function, so very easy. So that create function. It means function. So that function, so first f is the function, then is equal to that add the rate, then operator. Okay, so then x is the variable, independent variable. So now here we have to write the equation, right? So now I have already, so I'm just copy pasting all these things. So that is here, you can put that. Okay, so now okay, this is the variable. So now here is actually f, this is that function. Okay, now if I run the function, so that will, you can see like that. So these are the function. Okay, so this is the function at the rate f 1 by square root plus 2.0 log 10 equals like that. Okay, now so next step is we have to create the derivative. So df is nothing but what? So df is nothing but, okay, so this is small d, so we know, right? So by using central difference we can do that, right? So that we can use that formula by using central difference. Okay, so here we can use that by using central difference. Okay, so this is the derivative by using central difference. So that is the derivative. Now here we need h. So h is nothing but very small value, 0.00001. If we take that, so we can easily get the derivative, right? Now after getting the derivative, so we have to calculate f. Okay, so this is the Newton-Raphson method. So now we implement NR method. Okay, so if we implement NR method, so that will be what? F is equal to f minus that function value. So here f of f, okay, so that will calculate the function value divided by that df. Okay, so that we can calculate here. Okay, so now we can calculate, we can run that program. So first, okay, so that we got 0.06048. Now we have to check that whether we are getting that function 0 or not. So that f of f, right? So first we have to check, right? If we check that, so that is 1.7352. So now we have to do iteration. So now how do you do the iteration? For that, so we have to use for loop, right? So for loop here we have to use, so for I is equal to 1 is to, maybe you can 10 or 100 or 50, whatever iteration you want, you can do that, but there should be some criteria. Now here is end, right? End. So if you run that, you will see, so lot of, so 50 iteration is going on here, so we don't need all this, so we have to do some stopping criteria, right? So for that, initially, so whatever that f value is we are taking, so that f, okay, so f of that is also not required. Okay, so now here is the stopping criteria. So if we can use that if else statement. So if absolute value of that this f this f less than 1 e to the power minus 6 means 10 to the power minus 6. So that will break that loop, and for if we have to write end, right? If we run that, I can see that if we run that, you can see, so after 6 iteration, so we'll get the f value, right? So now here we are getting that f is means after 6 iteration, so 1 2 3 4 6 iteration, we will get that f value, right? So now if you print that nice way, so you can use that something, that formatting statement. So you can, if you want to learn how to nicely print the all these variables, so you can just take help, and if just type fprint, you will understand, you will know how to do that. So these are the statement. I have already written the code, I have that, okay, and then I'll write how to print. Okay, so I'm just putting here everything, right? If I do that, so these are the code. Okay, so these are the things. So I'm just using the two statement here. So one is, this is the formatting, another is this will give the value. Okay, now here for that f0, okay, so initial means what will be the previous value. So for that we need something like, so f of 0 is, we are assigning the value is equal to f, right? And if we run that, whether it will give the result, yeah. So see here we are getting, so here we have to put all this comma. Now if we run again, so you can see, say here, so this is the iteration number, then function value, fn value, and then function value, then derivative, then Newton-Raphson method, then what will be the fn plus 1. So now you can see in the last, that will be less than 10 to the power minus 6. So now that will be your friction factor. Now you can calculate that pressure drop. Okay, so now you can put here, so display, so one inbuilt command is there. So here, so friction factor, so print friction factor, so friction factor, you can use fprint also. Friction factor is equal to, so f is equal to, you can print that, so that disv of f. Okay, so that we can do. If we run that program, so we will get this. So f is equal to 0.01823. Now after that we can calculate del p, right? So now again I'm not typing here, so we have already the code. I did that code, so I just copy pasting here. So that is del p is the pressure drop, f l rho v square by 2d. Okay, now if we run the code, okay, so that will give the pressure drop. So pressure drop, okay, again, so it is not showing del p. Oh, okay, del p is showing here now. Okay, so we can every time that is calculating. So now here we can put at the end, otherwise whatever f is getting in the for loop, so that will give the del p. Now if you run that, so you will get, so del p is 7604.3. so that is the answer, that things actually asking, means what will be the pressure drop. So we are calculating the pressure drop 76043. Now we can put the display, we can here display here, so that here pressure drop in Pascal. Okay, so that PA, that will be del P. So if we do that, we will get a pressure drop. So we can do that, we can get that. Okay, so pressure drop will be this. We can just put semicolon, so that will not display. So now we'll get the del P. Okay, so that way you can write the code. So very easy code, we can easily do that, right? Now we can vary that epsilon also. So now if we vary, suppose if we put that epsilon, suppose if that is 0.0015 mm. So if we do that, so again we'll get different value. So see 116.1. So within 2 iteration, so we can get that ZP value. See here fixation factor is 0.26886. So now we can vary that for parameter, and if we vary parameter, we'll get different results. So if we have the code, so we can get that pressure drop for different variable. Okay, so that we can easily calculate the pressure drop. That's it. Thank you.